Hey there, it's Shannon Math Chick Myers. Today in our discrete math class, we are taking a look at sequences and series and products and the notation that goes along with these items. And we will need to get very, very comfortable with these things so that we can use mathematical induction as a way to verify math proofs about, or math statements about sequences. All right, so here we go. The main mathematical structure used in the study of repeated processes is the sequence. And the main mathematical tool used to verify conjectures about sequences is mathematical induction. A sequence is usually represented as a set of elements written in a row. And the sequence denoted A sub m plus 1, A sub m plus 2, all the way down to A sub, n. Each individual element, and we usually generalize that to some A sub k, is called a term. So the input or domain of the sequence is typically the set of non-negative integers or some subset thereof. Often we do have infinite series, but right now let's focus more on the finite series. I'll show you what they look like, but in this particular section, we're not going to focus a huge amount yet. All right, so these integers are what we substitute in for each of these k's. All right, or m's, whatever the subscript of the sequence is. The output of the sequence consists of a list of terms, depending on how many terms that you are finding. And sometimes that can be infinite. All right, so each output is plugging in something for the subscript. That's the input. And then the output is what you get as a result when you compute that. All right, so let's consider a function and a sequence that are very similar. All right, and then just to keep it, hopefully you're okay with this notation now. The upside down A is for any k belongs to the integers, k is greater than or equal to 1. That goes with the second expression, or the sequence one. Okay, so here we go. If we, kind of number our stuff here, let's do our y values kind of lower. So let's say that we'll skip one in between. So this right here would be 3, -3. And then for the x's, we'll just keep them as 1 per box or per line. And now for this one, so I'll do it the same over here so we can compare. And completing the labeling. So let's first work on f at x, all right? So the input is x, and then the output is the y value that corresponds to that x value you put in. So here there is a domain issue, right? What is excluded from this domain? So we're talking about this guy here. Beautiful. X can't be negative 2. Why? Awesome, because x equal to negative 2 yields a 0 in the denominator. Now, since that factor doesn't divide out, this results in a vertical asymptote at x equals to negative 2. So that'll be over here. Now notice we will not have that issue on the graph of the sequence because we start at k equal to 1 in our case. All right, that's the way I did the domain. Okay, so now graphing this one, if you find f at 0, what are we going to get? You plug in a 0 wherever you see an x, and you see we'll get 0 over 2, which is beautiful, 0. Notice we will have a horizontal asymptote at y is equal to 1, and that kind of gives us the framework for our graph. So completing a few more, computations, f at 1 is going to give us what? Beautiful. 1 over 1 plus 2 is 1 over 3. So we've got 1 and then a third is going to be maybe here. And then f at, I don't know, you want to take it to 4, is going to be 4 over 6, which is 2/3, right? So 1, 2, 3, 4, up here at about 2/3. So looking at something on the negative side to the right of the vertical asymptote, f at negative 1 is going to give us negative 1 over negative 1 plus 2 is positive 1. So we will get negative 1 over 1, which is negative 1. So negative 1, and then continuing, you'll see the graph looks something like this. Cool. All right, well, now what happens with this one is, we can plot some more points. You'll get the picture very soon. No pun intended. So let's also look at some negative sides. So f at negative 3 is going to be negative 3. Negative 3 plus 2 is going to yield a negative 1. So do you see we'll be out at the positive y value? So x is negative 3. Y is going to be positive 3, right? So this is going to be up here. Cool so far? And then we have this asymptote here. So what happens is, let's go ahead and do another value that's further to the left. And so let's do f at negative 6. So that'll give us negative 6 over what? Negative 6 plus 2, which is negative 4, which is positive 3/2 or 1.5. So going out to negative 6 and going to positive 3.5, we'll have a point here. So it'll look, something along these lines. I'll go a little beyond the grid. Cool? All right. Now, I really wanted to kind of emphasize what we were doing. We had an input and we had an output, right? So if our inputs were put in for the x's, correct? So I input 0, 1, 4, negative 1, negative 3, and negative 6. And then I got these outputs, which were my elements, some elements of my range, right? And I was able to make the graph from there, right? So with our sequence, what we're going to do is this. So now our input is k, not x, it's k. And our output is a sub k. Cool so far? All right, so we start out with our, we have a sub k is equal to k over k plus 2. So that's like our general term. We're only putting in positive integers. Sorry, forgot my k. So what is a1 going to be? Beautiful. 1 over 1 plus 2. Plus 2. So that gives us 1/3. Good, good? So inputting for k, we get the output of 1/3. So 1, and then 1/3 is about here. So do you see that this graph will be equivalent to the graph of f of x at all of the positive integers? Awesome. So continuing, I'll do a couple more so you can kind of get the feel for it. A sub 2 is 2 over 2 plus 2, which is 2 over 4, which is, oh wow, 1/2, see? So again, wherever there was a k, I put in the k value that I was interested in, and I got my term, okay? So this gave us that a1 was equal to 1/3. Over here, we had f of 1 ended up being equal to 1/3. Cool, cool? Okay, so moving along, just like, we were seeing from the other graph, if I put in 2, I get out 1/2, and then it's going to go along. What else did we find? At 4, we were at 2/3, so about here, and then at negative, we were not doing -1, so we can do a couple more at positive 6. Let's do a sub 6. That'll be 6 over 6 plus 2, which ends up being what? Good. 6 over 8, which reduces to be 3/4, right? So positive 6, we're at 3/4. So here, notice that this is the graph. You don't do anything in between, all right? And what you're going to see is you'll get closer and closer and closer out to a term output of +1, but you'll never quite attain it. Cool, cool? All right, so anyway, we only have 2 inputs missing. We might as well find them. So here we go. A sub 3, or 1, 2, 3, is going to end up being what? 3 over 3 plus 2, so 3/5. And then a sub 5 would be 5 over 5 plus 2, which would be about 5/7. And then 7 over 7 plus 2 is 7/9, so 0.777. So you get kind of the gist of it. Cool, cool? All right. So here we go. Let's take a look at some of the nuts and bolts here. So officially, in this text, a sequence is a function whose domain is either all the integers between 2 given integers, or all the integers greater than or equal to a given integer. So that's what's going to give you an infinite sequence. So here I was giving you sort of an simplified look. Non-negative integers or a subset is really the same way of saying this here, except I did them in different order. Okay? So just to kind of recap in the, variable format, we have for a finite sequence, it would have some starting input, right? Which will give you an initial term, right? So you'll have some starting input, and the value you get, which does not have to be an integer, right, is your first term, your initial term. And then you go on, and you do the next one, right? And you go in ascending order. And then any, random term in there, it could be our a sub k. And then you keep going until you get to your very last final term. Okay, so this is when it's finite. So here we would have our final term, initial term, so our initial term, let me do a different color. Our initial term is this a sub m, and then our final term of a finite sequence would be some a sub n. Now, these are just dummy variables, okay? They're just, you can pick whichever letters that you want to use. They're just arbitrary as long as you define them, okay? So these are finite, and each of the outputs, remember, are terms. So each of what I have listed here are the terms of the sequence, all right? So they're all terms. Now, an infinite sequence has some starting input, right? Our a sub m would be our initial term, right? And then, but here you just keep going, right? And you have, some general term. You could call it AK, AN, whatever. I'll just use K in this case. But the dots mean it keeps on going. That list keeps on going in that way infinitely. All right? So again, initial term. But you don't have this time a final term. Cool? All right, so let's practice. Please compute the first four terms of. Now, what is that notation? Do you remember? Beautiful. That is the floor of m over 4, right? And then you multiply that result by 4. So this one here, take a look at what your starting input is. It's greater than or equal to 1. So D1 is equal to the floor of 1 over 4 times 4. So I input 1 wherever I saw an M. Cool? All right, so now what is the floor of a quarter? Remember, that's equivalent to the greatest integer function, right? Evaluated at a quarter. So the greatest integer function is saying, hey, what's the greatest integer that you've attained? So a quarter is between 0 and 1, right? And so the greatest integer attained is 0, right? So then we would get 0 times 4, which is 0. Cool? All right. So now, what's D2? Beautiful. The floor of 2 quarters times 4, which is, well, the floor of a half, right? But that still hasn't attained 1. So the greatest integer attained is 0. So we still get an output of 0. D3, 3/4, the floor of 3/4 times 4, you still get 0, right, for the floor portion, and 0 for the term. But D4 changes it up a little, right? Because what do we get? Beautiful, 1 times 4, which is 4. So let me catch up in how we input these things. And if you were going to list the first 4 terms, you wouldn't ignore those zeros. You would say 0, 0, 0, 4. These are the first 4 terms of this sequence. Groovy? All right. So now this can be a little bit tricky. Find an explicit formula for the sequence. So you've been given how many terms? Well, we have, this would be, and this could change, right? It depends on, we haven't been told where this sequence starts, right? Does it start at 0? Does it start at 1? Okay, so the answers would vary on this one. So let's say that we start this one let's start this one at 0, okay? So we'll have A0, right? So we'll call our general sequence A sub k, right? So A0 is 0, and we have A1 is negative 1/2, A2 is 2/3, A3 is negative 3/4. So do you see that this is changing signs? So in math, we call that an alternating sequence. So this last one I'm working on so far is A4. The next one, negative 5/6, would be A5. And then 6/7 would be the output associated for our k equal to 6, right? So A6. All right, well, you know it's going to alternate. And so remember that if you raise -1 to an integer, you're either going to get -1 or 1, right? So what we have to play around with is, okay, well, what's happening here, right? And remember, you got to think of it, we want to find some A sub k, right, equal to something in terms of k. If you had chosen A sub m, you'd be looking for writing it in something in terms of m. So what do you think? The very first one isn't going to help us as much. But if you're inputting, so let's take a look at starting at the second one without worrying about the -1 part. In fact, we know there's going to be a fraction, correct? So we'll write in our fraction. We'll write in -1. It's going to be raised to some expression in k. We just don't know what yet. All right? So if I plug in a 1 for k, so I'm looking at this one, A1. Well, the formula that would work would be just to have this right here be k, correct? Remember, we're going to take care of that negative at the end. All right, well, what would I have to do for the denominator? Beautiful. I would just need to add 1 to k. So that's a proposed general term here. So what do you think? Does it work for the next one? Again, ignore that -1. So for A2, right? A2 would be -1 to something, right? And then if I did it with this formula I had done, it would be 2 over 2 plus 1, which would be -1 to something times what? Beautiful. 2 over 3. So that works out. So I think we're going to have that be our general term. What's happening with that -1? It's alternating. So remember, when you raise anything to the 0 power, what do you get? Beautiful, +1. So when do you have negative outputs? When you are on an odd input, right? When k is 1, when k is 3, when k is 5. Make sense? So let's see if that'll work. -1 to the k times k over k plus 1. So for A2, we'd have -1 squared. And that would equal to, I'll just swap this around since we figured it out. That would equal to 1 times 2 over 3, which is 2/3. And that definitely checks out, right? Cool, cool. So we had a little bit of scratch work over here. And then we have to identify what's going on with k, right? So what does k start with? K is an integer, right? So for any k that belongs to the set of integers such that k is greater than or equal to 0, right? Or you could write it like this: a sub k equal to -1 to the k times k over quantity k plus 1. And you could say this. You could say for k equal to 1, 2, 3, ... And actually, what did I kind of screw up on? I mean, k is bounded, isn't it? Where does k stop? It stops at 6, right? So how do I have to change the one above? Instead of having k greater than or equal to 0, what do I have to say? K is an integer that is between 0 and 6 inclusive. Cool, cool? All right. So let's keep going. So here, either one of these would work out just fine, right? So I'll just box both of them with our little adjustment here. And let's move it along. All right, so our next definition deals with summations. All right, so if m and n are integers and m is less than or equal to n, this symbol, which is red, the sum, or really most properly summation, which basically means add them all up, from k equals m to n of a sub k is the beautiful sum of all the terms am, comma, a sub n plus 1, comma, a sub n plus 2, comma, all the way to a sub n. So it's basically, you add up all the terms of the sequence, right? So the expanded form, which is very useful. A lot of people, they don't want to expand these things out, but when you are adding summations or something like that, they can change quite a bit when you do some algebra with them. So the expanded form of the sum is a sub m plus a sub m plus 1 plus a sub m plus 2 plus all the way down to plus a sub n. So writing it together, we would have the summation from k equals m to n of a sub k equals the initial term, a sub m, plus the next term, which would be a sub m plus 1, plus a sub m plus 2, all the way down to plus a sub n. Cool, cool? Awesome. All right, now k is called the index of the summation. So it's telling you where to start. Well, actually, m tells you where to start, but k tells you where to plug in these integer values that are in the domain, all right? And m, the initial limit of the summation, and n, the upper limit. Now, if you have an infinite sum, you have no upper limit of the summation. All right, well, let's check out this one. Again, using m's, which of course I'm having trouble saying today. So here we go. Please compute the summation from m equals 0 to 3 of 1 over 2 to the m. All right, so let's do it. The summation from m equals 0 to 3 of 1 over 2 to the m equals, well, let's look at the expanded form. So the very first, the initial, what? The initial term will be the term which occurs when I plug in 0 for m, right? So the initial limit of the summation is, beautiful, 0. So we would have 1 over 2 to the 0 plus, awesome, 1 over 2 to the 1 plus 1 over 2 squared. And that upper limit of the summation was 3, so we're almost done. 1 over 2 cubed. Cool so far? So I'll just highlight what was going on here. Yeah, I did that for term, didn't I? So the 0 here is the initial limit of the summation. Cool. And then the n was the upper limit of the summation. So 3 is that upper limit. And the index of this summation, is m. Whoa, sorry. Is m. All right, so you can't depend on these, letters given and these definitions not changing. That's just not what happens. So you need to be flexible, all right? Okay, well, let's finish up and figure out what this sum actually is, right? So what's going to happen, we'll get, if we get a common denominator, what would that be? It'd be 2 cubed, right? So here, the first term has 0 factors of 2, right? So it would be 1 times 2 cubed plus 1 times 2 squared, because only 2 are missing, 2 factors, plus 1 times 2 to the 1, plus 1 times 2 to the 0, all over 2 cubed, which is, good, 8 plus 4 plus 2 plus 1 over 8, which gives us a result of 15/8. And we're done. So the output of that finite sum is, and actually it's called the nth partial sum if you start it at the very first possible domain value, but that's more of a Calc 2 thing. So 15/8 is this partial sum, right? When we take m from 0 to 3. Cool? Okay, so now we just want to make sure we can go both directions. We went from looking at the sum and then computing it and getting the result of the sum. And now we want to take the terms. These are each terms of our sum, right? So again, it's really just going to depend on where you start, all right? So there would be multiple possible results for this. Let's go ahead and suppose that we're starting this sum at, what do you think? Let's start it at 1, okay? So if we started at 1, let's use, I don't know, I this time. So I equal 1 to 3, right? Because this would be A1, A2, and A3, okay? And then the plus signs make it a summation. Cool, cool? So if we do that, what do we need to do? Well, we'd have the sum from I equal to 1 to 3 of, well, we have a 2 being squared and then minus 1, then plus a 3 being squared minus 1, plus a 4 being squared minus 1. So here, aren't we going to be adding 1 to I, squaring it, and then subtracting 1? And then if you kind of do a mental check there, you'll see that that works out, right? And then what happens if I simplify that? Well, this would end up being the sum from I equals 1 to 3 of, good, I squared plus 2I plus 1 minus 1, right? Which in turn is equal to the sum from I equals 1 to 3 of I squared plus 2I, right? And you could also factor out that I and write it as well. I'll just keep it like this. Cool, cool? All right, and remember, the answers will vary depending on what letter you choose to serve as the index of your summation and where you choose to start. What is your initial initial limit and what is your upper limit? Okay. All right. So next up, well, we also have a shortcut for writing a string of products, right? So if m and n are integers and m is less than or equal to n, the symbol, so it's like a pi, and that would be from, actually, let me write that higher, from k equals m to n of a sub k, and it's read the product from k equals m to n of a sub k is the product of all the terms in the sequence. am plus 1, am plus 2, all the way to a sub n. So the expanded form of the product is a sub m times a sub m plus 1 times a sub m plus 2 all the way to a sub m, all of those being products. All right, so this is how it would look all together. And notice the dots are at the same level of where the multiplication symbol would go. Whoops. Cool, cool? All right, so let's practice. All right, so we're going to compute the product from j equals 0 to 4 of -1, that quantity raised to the j. So be careful when the negative is in the parentheses, you're going to have something that will alternate, right, when it's raised to a power. So let's check it out. So this will be -1 to the 0 times -1 to the 1 times -1 squared times -1 cubed times negative 1 to the 4th. All right, so what's that going to give us? Positive 1 times negative 1 times positive 1 times negative 1 times positive 1, right? And this is beautiful, positive 1, because there's an even number of negatives. Cool, cool? All right, so next example, this will be pretty similar. Let's practice starting at a different index, all right? So here, it's going to be a little bit different because we will have a product instead of a sum, but it's the same expression inside. What if we go ahead and start at 0? All right, so let's do this. Let's have it be, I don't know, if we start at 0 and let's use a different letter, we can do that, right? So let's say, we're going to say K is equal to 0, 1, 2. We have 3 terms. So this now would be our A sub 0, A sub 1, and A sub 2. Good so far? All right, so putting it all together, we would have the product from K equals 0 to what? Good, 2. And then that is going to be of what? So when you plug in a 0, you're going to need 2. Beautiful, add 2. So this would be K plus 2, the quantity squared, minus 1, right? All right, well, let's simplify that a little bit. That would end up being the product from K equals 0 to 2 of, so expanding the square, we'd have K squared plus 4K plus 4, right? And then minus 1. And that in turn would give us the product from K equals 0 to 2 of, good, K squared plus 4K plus 3, which could be factored, right? But we'll just keep it like that for now, all right? All right, cool, cool. So next we have some theorems about, and I'm not going to prove these. We have way too much to do today, all right? I have a feeling we'll be proving some of this stuff. But again, if we now have 2 sequences, all right? And if they have the same, you have to make it where they have the same summation. They have to have the same index, okay? And they have to have, well, we do different things with them, but basically you want to make them have the same starting number, all right? The same initial limit and then the same upper limit, okay, in order to do this first property, any of these properties. No, the first and the third property, all right? So you've got A sub m plus 1, all the way down to A sub n, and B sub m plus 1, all the way down to B sub n are what do you think? Beautiful sequences of real numbers, and C is any real number, then the following equations hold true for any integer n greater than or equal to m. So if you have the sum of 2 summations and all the conditions are met, it's the summation of the sum. Notice that you have to have parentheses when there is a sum, because otherwise you would be implying that if you didn't have these parentheses here, you'd be implying that you'd be summing A sub k and then to that adding some sequence, okay? So make sure your grouping symbols are good. But when you have a product, you don't have to put parentheses in there, okay? It's assumed that Notice that for summations, you do not see a formula for the summation of a product unless that product consists of a constant times a sequence, all right? So keep that in mind. So here you can pull a constant in or out of a sum, right? And then if you're multiplying two of these products here, right? Then it ends up being the product of the product. Cool? Of the sequences. The product of the product of the sequences. Okay, so here we go. A dummy variable is a symbol that derives its entire meaning from its local context. So I don't know if you've done any parameterization, but when you pick some t, right, instead of letting something be in terms of, say, x or y, right, when you're solving a system of equations and it's dependent, you've parameterized it, so t is a dummy variable, right? So we use a lot of times these dummy variables with summations. So a sum or product can look a lot different when a change of variables is made. So just to give you a sense of a dummy variable, let's look at the summation from I equals 1 to, I don't know, let's do 4 just for the heck of it, of I squared. Good so far? So that would be what? 1 squared plus 2 squared plus 3 squared plus 4 squared. Good so far? And that, of course, is equal to what? It doesn't really matter. Actually, it doesn't even matter what it equals. Now, let's write the summation from j equals 1 to 4 of j squared. I mean, do you see that it looks a lot different, doesn't it? But what happens with the output? It's the same output, right? Each term of the sum is exactly the same, right? And so that's kind of, one way to think about dummy variables. You'll get the same result. And so we will often, use dummy variables so that, for example, in an integral, right, that has a variable in it, like with the second fundamental theorem of calculus. If you have that and you are, you would have in your integral, right, the integrand would have a different variable, but it's really just a dummy variable in there. Cool? Okay, so basically what we found here is we found that the sum from I equals 1 to 4 of I squared is equal to the sum from j equals 1 to 4 of j squared, right? So let's take a look at how we can transform, these symbols by making changes of variables. So for this product here, we want to change I to k plus 1, right? So first of all, let's take a look, all right? It's always good to isolate each variable. So if I is going to equal to k plus 1, well, that's true if and only if what? K equals what? Beautiful. I minus 1. Good so far? All right. So now here I've got this product, right? So I need to switch it around. So we need to figure out, okay, what is going to be, we know that we're going to have the index of the summation be I, right? Well, if the original starts at k equal to 1, what will happen? So when k is equal to 1, what happens to k plus 1? K plus 1 is equal to, awesome, 1 plus 1, which is 2, right? So the initial limit of our product is going to be 2, right? And then what are we going to go to? Well, here we went to n, right? So for k equal to n, k plus 1, plugging in n for k, we get this, right? So we go to n plus 1. Groovy. Well, now we know what k is, right? K is I minus 1 because we already looked at that. So on the denominator, we'll have I minus 1, the quantity squared, and then we're going to be adding 4. So simplifying, what are we going to get? We'll still have our I minus 1 in the numerator. And then in the denominator, what's going to happen? We'll have I squared minus 2I plus 1 plus 4. Oops. So that in turn will be good. We'll have our I minus 1 still over I squared minus 2I plus 5. Cool, cool? All right. Very good. How are we doing so far? So example 8, let's look at this summation, all right? And so here, it's a different skill. We want to write this as a single summation. So the first thing I'm checking is both of them are using I's, all right? And them being the summation symbol. And then both of them start at 1 and both of them end at n, all right? So what we're going to do is this. We're going to use that one property, right, where we can write the sum of two summations as the summation of the sum of the sequences. So this is what will happen. So we'll have the sum from I equals 1 to n of 1 over... Oh, I'm very sorry. There's a typo here. This should not be n. This should be an I. Right here. Sorry. I'll do it in black or in red so you can see that it was an error. This should be an I. Cool, cool. All right, so 1 over I plus 1, the summation from I equals 1 to n, plus the summation from I equals 1 to n of negative 1 to the I over I plus 1. Well, notice they have the same denominator, right? So, and we just compared the indices of the summations were the same, and the initial limits of the summations were the same, and the upper limits of the summations were the same. So that means we can write it as one happy summation where we are summing 1 over I plus 1 plus negative 1 to the I over I plus 1. But what is that? Can't we take a look at this? Actually, let's write one more thing. We can simplify this to one happy fraction, right? The sum from I equals 1 to n of 1 plus negative 1 to the I over I plus 1. Okay, well, we're good so far, right? But we can make that one a lot easier. Let's check it out. And if you're taking Calc 2 right now, this might be helpful unless you're past it. But when you take Calc 2 this and differential equations, this is a useful skill. So here we go. Let's expand this summation out a little bit. Well, if I plug in 1 for I, right, for my first term, what's going to happen? I'm going to have 1 plus negative 1 to the 1 over 1 plus 1. All right, next term is plugging in 2 wherever we see an I. So the 1 we plugged in was here. Okay, so the next one would be 1 plus negative 1 squared over 2 plus 1. Cool so far? Next up, we'd have plus 1 plus negative 1 to the 1 over negative 1 cubed, over 3 plus 1 plus 1 plus negative 1 to the 4th over 4 plus 1, and you'd be continue in this manner. So let's see what happens to these things, all right? So let's check it out. Well, this would be, I had an odd value I was plugging into the index, and so I ended up getting 0 over 2, right? And then when I plugged in an even number, what did I get? I got 2 over 3, right? Because that negative 1 squared is 1. And then over here, I'm back to getting a 0 over whatever, 4. And then look, plus 2 over 5. And it would keep going on in this manner, right? So all of the odd terms are zeroing out, right? And we have a 2 in the numerator. So this would end up being 2 times 1/3 plus 1/5. Do you see what's going to happen? We didn't do those up here, but it'd be 1/7 plus 1/9 plus ... Groovy? So now we have to figure out that new general term, all right? So that new general term, and remember, we don't want to skip numbers on our index. So this would end up being what? We always have to get an odd, right? So what did we say, in Mathies, how do we define an odd? Beautiful, 2n plus 1. So let's look at that. So 2 times the summation from I equals 1 to n. 1 over, so now we don't want to use an n, right? We want to use an I. So 1 over 2i plus 1. So for I equals 1, what would we get? We get 1 over 2 plus 1, which is 1/3. Cool. For I equals 2, we get 1 over 2 squared plus 1, which is 1 over 5. Awesome. So do you see this one's working out? So that is our result. We can box that, and we're good to go. All right. Now, if you're going to go into statistics or anything at all, or some kind of probability-based mathematics, this is stuff that you'll look at. You'll look at a lot of, infinite sums and rewriting stuff, and it's all very groovy. Okay, so another definition. For each positive integer n, the quantity n factorial, and it's denoted with an n and an exclamation point. That means n factorial in math is defined to be the product of all the integers from 1 to n. So it's basically decreasing products, okay? So n factorial is n times quantity n minus 1 times quantity n minus 2, all the way down to 3 times 2 times 1. Now, 0 factorial, which is denoted, of course, 0 with the exclamation point, is defined to be 1. Well, if you're dealing with decreasing products, what is the identity element for multiplication? Beautiful. It's 1, because you multiply anything by 1 and you get that same thing that you started with. All right, well, let's practice doing these factorials here. So 10 factorial over 8 factorial basically is going to be the decreasing products, right? So 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, that looks like a decimal, sorry, times 2 times 1, all over 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? So notice what happens, right? Don't all of the ones starting with 8 and going to the right divide out, right? So this will actually just be 10 times 9 over 1, which is 90, right? Okay. Well, what about this next one? Quantity n plus 2 factorial over n factorial. Well, isn't that kind of like this one here that we just did? I mean, couldn't we rewrite 10 factorial divided by 8 factorial as 10 times 9 times, 8 factorial over 8 factorial? So what I did here is I just said, oh, okay, well, this here is 8 factorial, right? So, okay, well, the 8 factorials divide each other out, right? And then, of course, we just get 90 like we had gotten before. So now, oftentimes, we don't know what value of n we're dealing with, right? So if we come over here and if we think about what happened, what did we do? The 10 on the left side and, the 10 and the 8. Well, isn't 10 8 plus 2? So I did this problem like this on purpose. So here, if 10 is 8 plus 2, so 8 is the n and 10 is n plus 2, couldn't I write this as n plus 2? What would the 9 be? Awesome. It'd be n plus 1. Notice there's no factorial. And now I can say times n factorial all over n factorial. I mean, isn't that what we did over here, right? So the beauty of that is, so let's get an equivalence here. This quantity n plus 2 factorial is equivalent to this. And the evil plan here is we want to be able to divide out the n factorial that's in the denominator. And that's why we made those changes. So now that we wrote it like this, we've divided it out. And so what we found is that n plus 2, that quantity factorial divided by n factorial, is just n plus 2 times n plus 1. So again, you'll be using this skill in calculus 2 for sure when you are testing infinite series to see if they converge or diverge, right? And with power series and all that. So Here we go. And then we can double check. If our n was 8, right, we would end up getting 8 plus 2 is 10 times 8 plus 1 is 9. And then we would have, beautiful, 90. So it checks out, but this is the result in general. Cool, cool? All right. And if you expand, you could expand it if you wanted. I'm just going to leave it in factored form. Okay, so now let's check out our next exciting item. Let n and r be integers with m less than or equal to r less than or equal to n. The symbol red n choose r represents the number of subsets of size r that can be chosen from a set with n elements. Okay? And then a formula for computing this for all integers n and r with 0 less than or equal to r less than or equal to n. N choose r is equal to n factorial divided by all of this stuff, r factorial times quantity n minus r factorial. Note that the factorial, it's symbolizing, it's symbolizing decreasing products. So it's not like you can distribute that factorial symbol in there, okay, in that difference. You have to complete the difference first, all right? So example 10, please compute the following. So here, 6 choose 4. 6 choose 4 is equal to, so my n in this one is 6. So 6 factorial over the number of subsets we're dealing with, which is 4 factorial. And then we also in the denominator have 6 minus 4, that quantity in factorial. Cool, cool? So this will give us 6 factorial over 4 factorial times, beautiful, 2 factorial. Well, we'll use that trick from last time. 6 factorial, 6 times 5 times 4 factorial divided by 4 factorial times 2 times 1. And so this 6 factorial is equivalent to this expression here, and thus I can divide out the 4 factorial, and at the end of the day I'll get what, 30 over 2, which is 15. Cool so far? All right. Okay, well, again, I have an evil plan for you to see how this would be. Do you notice that if n was 5, right, I'd have the same situation as in number 1, wouldn't I? So let's check it out, all right? It's going to look a little more complicated. We'll have n plus 1, that quantity factorial, over, now we're choosing n minus 1, so n minus 1 factorial, and then we've got to compute the difference between n and r, so we would have n plus 1 minus n minus 1, and that whole quantity would be in factorial. So let's see what happens. Simplifying, we still have our n plus 1 factorial here over n minus 1 factorial. Well, n minus n is 0, and then 1 minus negative 1 is 2, so we'd have 2 factorial. Good so far? All right, so now you want to switch around the larger factorial, okay? So n minus 1 factorial is the smaller one. So we're going to leave that alone, but we want to rewrite n plus 1 factorial so that we can have an n minus 1 factorial in it so we can divide out the n minus 1 factorial. So that's a, needed a big breath for that one. All right, so here we go. Well, we'd have n plus 1 times n times, good, n minus 1 factorial. So that's like what we did over here on the left. All over, you move that equal sign over, all over n minus 1 factorial times 2 times 1. So n plus 1 factorial, I rewrote like this. And so now we're going to be able to divide out the factorials, and we'll end up with n times n plus 1 over 2. So let's test it out compared to the last one. If n was 5, right, we'd have 5 times 6, which is 30 over 2, which is 15. So cool. It checks out. Groovy? All right. So now let's look at this kind of cool application. All right. So there's a lot of computer science people in here, and you probably already know this, but we'll take a look at it anyway. So here we go. We want to convert 205 and base 10, that's what the lowered subscript means, to binary notation. So we want to basically convert to base 2, which is why we would use repeated division by 2 to make this conversion. All right. So consider 205. All right. Well, if 2 is the divisor, right, couldn't I write it like this? So my very first division by 2, I'm really writing it in that dq plus r format, because what we're interested in for coding often is those remainders, right? So we'd start with what? 102 times 2 plus 1. Do you see that's equivalent to 205? So the remainder, when I do this computation, so that initial remainder, so they do it in brackets because that's what you used to have to do for coding. It used to be like the computers couldn't do subscripts, okay? So that remainder at 0 is equal to, beautiful, 1. Good so far? Awesome. So now what we're going to look at is this. So our very first deal is we rewrote 205, okay, as this whole quantity here, all right? And we figured out what that remainder was when you divide 205 by 2. So now you keep going, all right? So now we look at 102. So what would I multiply 2 by to, and then what remainder would I have? So do you see that 102 is equivalent to what? 51 times 2 plus 0, right? So this 102 is equivalent to this quantity. Okay, so this quantity is the 102, but wasn't that multiplied by 2 and then we had a 1 added to it as well? Because we want to keep rewriting equivalent statements, right? So simplifying, what would happen? We would have 51 times 2 squared, right? Plus 0 times 2 plus 1. which in turn will just give us 51 times 2 squared plus 1. Now, let's talk about the remainder we got when we divided 102 by 2. So this remainder, call it R at 1, is equal to 0 because we got a 0 here, right? This one was 1 because we got a 1 here. The only remainders we'll get will be 0 or 1 because we're in base 2. Cool, cool? All right, so I'm going to continue working on these. I'm going to go a little bit faster so that people don't get bored. So I'll stop talking so much. But if you want to slow the video down, you should be able to in your commands. Okay? All right, so let's include all those powers of 2. So 205 base 10 is going to be, so drum roll here. So I'm looking at these things here, and I'm going to include the missing powers of 2 as well. So we're going to have 1 times 2 to the 7th, right? 1 times 2 to the 6th. 2 to the 5th and 2 to the 4th are missing. So there will be zeros as placeholders there, right? And then we have 1 times 2 to the 3rd. We have, sorry about the dogs, 1 times 2 squared. 2 to the 1 is missing. And then we have 1 times 2 to the 0. Cool, cool. And that's in base 2. That's in binary. Groovy? All right, so here you go. A computer science application for you. Now here's utilizing that stuff, okay? Here is an algorithm I thought you might be interested in. Decimal to decimal meaning base 10 to binary conversion using repeated division by 2. So given an input A, which is a non-negative integer, A base 10 is equal to the remainder at k times the remainder at k minus 1 times the remainder at k minus 2, all the way down to remainder at 2, remainder at 1, remainder at 0, and that's in base 2, all right? Or you can rewrite it that, one way that I had written it to get it as well. Cool, cool? So that's all we have for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe. That would be helpful in letting me continue to run this channel.